that Cx is n degree polynomial, so just correct that error. So it is a n minus 1 degree polynomial. So what is the criteria that any n minus k degree polynomial is a generator matrix for a n comma k code? So I told you that any factor of x to the power n plus 1 with degree n minus k is a generator polynomial for a cyclic code of n comma k. So if this is a very important for exam point of view. If in an exam we ask if we want to design a 7,3 cyclic code, if gx can be used as a generator polynomial, well gx is x4, x3, x2, x1. So step 1 is to check degree of this polynomial. So if we check, the degree is 4, which is equal to n minus k, that is 7 minus 3. So degree, one first criteria is satisfied. The second criteria is it should be factor of x to the power n plus 1. So the next step is to check whether this generator polynomial is a factor of x to the power 7 plus 1 or not. So how to check that? In order to check that, we have to see the remainder of x to the power n plus 1 divided by gx. So the remainder is 0, it means gx is a factor of x to the power n plus 1. So let us check that. We write gx here, we write x to the power n plus 1 here, and we divide it. And when we divide it, we have to first multiply it with x cube, correct? So here we can write x to the power 7, x to the power 6, 5, 3. So 6, 5, 3, 1. Next is to multiply it with x square. So when we multiply it with x square, this is x to the power 6 plus x to the power 5 plus x to the power 4 plus x square. So next we multiply plus 1 with 1. And we see the remainder is 0. So this polynomial satisfies the two conditions that it has degree n minus k and it is a factor of x to the power n plus 1. Therefore, it can be used as a generator polynomial for a 7,3 cyclic code. So this is the two step you have to check whether any polynomial could be used as a generator polynomial for n comma k cyclic codes. First check if the degree is n minus k and second check if the remainder is 0. And generally it has this type of form 1 plus x to the power n minus k is here, as you see here. 1 x to the power n minus k and there are some other terms. Therefore, this is our conclusion that x to the power 4, 3, 2, 1 is a valid generator polynomial. This point is checked, this point is checked. Therefore, x to the power 4 plus x to the power 3 plus x to the power t plus 1 is a valid generator polynomial for n comma k cyclic code for 7,3 cyclic code. So this is a very important for the exam point of view. So just remember this. Then we discussed that what is the non-systematic way of generating linear cyclic codes. We have to multiply our code word polynomial with the generator polynomial. Once we find the generator polynomial, we have to just multiply it with dx. But this is a non-systematic cyclic codes. And in order to generate the systematic cyclic codes, what we have to do? We have to use this formula. Correct. Cx is x to the power n minus k dx plus rho x, where rho x is remainder of x to the power n minus k dx dx. So we discussed that we can either follow two approaches. First, we can take all the possible dx's, yani all the possible data code word, and we can apply this equation and find out the code polynomial. Or we can, because the cyclic codes are subclass or linear block codes, so for this each cyclic code there must be a generator polynomial or generator matrix also, because each cyclic code is a subclass of linear block code. So systematic generator matrix, if you remember, has this form. So in cyclic code, what we do, we first find out the gx. These are the steps. First, find out gx, and second, find the generator polynomial. And the generator polynomial can be found. Generator matrix can be found using this generator polynomial. This is parity polynomial. So generator matrix is I and P. So P can be found, the parity matrix can be found using parity polynomial. So for this I have discussed in the last class that we will find out the first row of this parity matrix by putting dx is equal to 1000 for if we have a 7,4 code. So let's discuss this concept once more because this is an important concept. So in order to find the encoder mapping means how each data word is mapped to a code word. So in order to find such mapping, first we find out what is the generator polynomial. Second, we try to find the rows of the generator matrix. Okay, so just discuss this concept. So if we want to have a n comma k cyclic code and we want to derive an encoder map, this type of mapping, that how each data word will be mapped to a corresponding code word. The tedious way we have discussed in the previous class, that we will use this equation for each dx and we evaluate rho x for each value of dx. That is one way. And the second way is just to find out the rows of this generator matrix, and then when we get this generator matrix, it is easier to derive the using this formula. So the first row of any first row of P, because we know what is I. I is a K cross K identity matrix. So it is easier. Just we have to find out the parity rows for the parity matrix. So first row of parity matrix P is nothing but remainder of x to the power n minus 1 divided by gx. Because if you remember in the last class, the row x is a remainder of x n minus k dx gx, right? So if this is our first dx 1 0 0 0, what is its value? X to the power k, correct? 0 1 2 xk minus 1, sorry. So the first row of P is remainder of x to the power n minus 1 gx. The second row of P is remainder of x to the power n minus 2 divided by gx. Up to we have to go for the kth row of P, that is remainder of x to the power n minus k divided by gx. So let's take an example. If we want to find out the generator matrix for 7,4 code, what we have to do first, find out the generator polynomial. So is this a generator polynomial? Because we have seen that x to the power 7 can be written as, we said both can be used as a generator polynomial. So let's use this as a generator polynomial and try to find out corresponding generator matrix. So generator matrix will have this form: 4 comma 4 identity matrix and a parity matrix, right? The dimension of the parity matrix is k cross n minus k, 4 cross 3. So we have to find out the 4 rows of this P. And I told you in the last, this first row of P is remainder of x to the power n minus 1 divided by gx. So the first row can be found by deriving remainder of x to the power n minus 1 means 6, and gx is x cube plus x plus 1. So just divide it. All this concept is discussed in the last class, but I am just reiterating again so that this is very important, because it is very important. So this is cancelled. We have x4 plus x cube. Now we multiply it with x. It is x4 plus x cube plus x. x4 plus x square, excuse me. So we have x cube plus x square plus x. And we have to divide it with x cube plus x plus 1. If we take it 1, we already have this plus 1 x cube plus x plus 1. And now we have this cancelled and x square plus 1. So remainder is x square plus 1. So the first row corresponding to this will be, because it is x cube plus 1, it should be 1, 0, 0. Sorry, it is x square plus 1. So it should be 1, 0, 1. So the first row of the parity matrix is, we know the identity matrix of, so the first row is 1, 0. Similarly, what would be the second row? Second row is remainder of x to the power 5 divided by gx. Third row is remainder of x to the power 4 divided by gx. And the last row will be x to the power 3 divided by gx. Because we want to find out the fourth rows. And if we solve it, you will get that this is this. The answer of this will be this. And so what is corresponding row? 0, 1, 2, 3. The 1 is on this place. 1 is on this place. Sorry, and 1 in this place. So 1, 1, 1. 0, 1, 2. Because it is only parity matrix is a 4 cross 3 matrix. Okay, so each is 3 bit long. 0, 1, 2 means 0. Here you have to put 1 and 1. And this is 0, 1, 2. So 1, 1, 0. So now your parity is derived. Parity matrix is with you. You have to write 1, 1, 1, 1, 1, 0, 0, 1, 1. So once you get your generator matrix, now it is easier for you to derive your your encoder mapping, because it is a 7, 4 code. What are the all possible combinations? 16 possible combinations, and corresponding to each D, you have to multiply it with the generator matrix, which we have found here. So we have seen that cyclic codes, we start with the generator polynomial, then we derive its generator matrix, and once we get the generator matrix, we get the encoder mapping, a table. This is your encoder table. How your each D is mapped to each C. So this is the encoded mapping, right? Now you have your encoder mapping. But how to implement this encoding circuitry in hardware. So let's discuss this. So we have to now discuss what is the encoding circuit for the cyclic codes. So it is mainly made of shift registers and mod 2 adders. These are adders, these are shift registers. So let us suppose we are taking a generator polynomial gx as x cube plus x square plus 1 for 7 comma 4 cyclic codes. Always remember that this is a very important type code because x to the power 7 we have to first find out what is its generator polynomial. Generator polynomial is a factor of x to the power n plus 1 and we know that its factors is this uh, 1 second x cube plus x. So both can be used as generator polynomial. So we are using this as a generator polynomial for this first example, and in the next example we will use the other generator polynomial. So how would you design the hardware circuitry for such a scenario? Just I will place it here. Just write your generator polynomial in opposite in the reverse order 1 plus x square plus x cube. Okay, so what is its corresponding? 1 plus x square plus x cube means 1 0 1 1, right? So wherever there is 1, just put a flip flop 1. There are 3 ones, put 3 flip flops first or 3 registers first. So you will put 3 registers and then wherever there is 1, put a XOR. So first place there is 1. In here you don't have to put any XOR wherever there is 1 after this point. So just here you don't need because 1 0 1. So now you have to put a flip flop. Now you have to put a flip flop or shift register. So this is your 1 0 1 1 shift register. These are registers, and your data bits you apply from here. So 1 second, I have to change the directions of this. Excuse me for that. So we put our data word like this, and then your data word goes in that direction. And how you put your data word? The question is first we insert the MSB or LSB. So if your data word is 0, 1, 1, 0, we put first its MSB. This is your MSB and this is your LSB. So we start with MSB first. So we put the MSB and this is your LSB, right? So MSB here. Now we start making the table. So this is your message M, and initially we assume that all the registers have 0 state. So put this is P0, P1, P2. So this is state P0, this is state P1, and this is state is P2. The output of each register. And now we start making the mappings. So this is M, this is P0, this is P1, this is P2. So first, initially all are 0, and then we insert a 0 here. Okay, so we just remove all of this. This is just to make the circuitry. Since it was x cube plus x square plus 1, so we just put a shift register here corresponding to x cube, x square, and 1. And wherever there is 1, we put a XOR circuitry. You can assume it at 1 0 1 1. So 1 0, 1, 1. See, wherever there is 1, there is some circuit, these lines. Corresponding, if there is 0, there is no XOR. So we remove this. Once we design this circuitry, we don't need this. Now we want to make the table. So first we enter 0, and 0 is now XOR with P2, and P2 is 0. So 0 XOR with P2 is 0. Now what happens? What is P1? P1 is same as P0, correct? Because it's a shift register, so whatever value P0 had previous time instant, P1 will be currently, the value of current P1 will be that only. So your P0 is this. And what is your P2? P2 is, if you see, your P2 is your P1 XOR with this value, correct? So whatever value is coming from here, because we have entered 0, so zeros are coming, right? So 0 XOR with P1. 0 XOR with P1. P1 XOR with 0 is 0. Next we entered 1. 1 XOR with P2 will be P0. So P2 is 0. So it will be 1. And now P1, because P1 and P0 is acting just no XOR between them. So whatever value was at the previous instant for P0 will be now for P1, which is 0. Now what value P2 has? Because now you have entered, so you have to change it. Because now you have entered 1. So because this 1 has gone with 1. Once you enter 1 and you take its XOR with P2, it is 1, right? So now 1. So now you have to, P2 will be P1 XOR with 1. So P1 XOR with. Now what will be your next data value? Your next data value is 1. So once you enter 1, 1 will be first XOR with P2, so it will enter 0. Because 1 XOR with P2 is nothing but 0. And P1 is same as previous P0, and your 0, this P2 is P1 XOR with 0. P1 XOR with 0, it is 0. And then next, your last LSB will enter. So you have to first remove it. And you have to enter 0. So when 0 enters, it will first XOR with P2. So it is 0. So all the inputs are 0. So when you enter 0, it's 0. Your 0 goes here because your current P1 is your previous P0, and your current P2 is your previous P1 XOR with 0. That is 1. So now you have seen that the parity, the P0, P1, P2 is 0, 0, 1. Okay. So this is your parity bits. And what was your data word? 0, 1, 1, 0. So initial k bits will be same. So what is its corresponding code word? Code word will be this and your parity bits. P0, P1, P2. So you have to write P naught, P1, P2. Just check the code word corresponding to 0110. So you have to start writing this, okay? P naught, P1, P naught. So first, if you want, so what is the whole summary of this? That this is your encoder circuitry, and if you want to find out using this encoder circuitry what is the code word, so you first enter your data word. So initial data word will be same, and then the output at the last of this gives you P naught, P1, P2, and you write it like this: P naught, P1, P2. So it is 100. So your code word corresponding to this data word will be this. So this is how the encoder circuitry, hardware circuitry works for the cyclic codes, which is made of shift register and modulo 2 XOR gates. So it is like that. Do you have any confusion? Similarly, one can also find out the table or the P naught, P1, P2 value for the generator matrix x cube plus x plus 1. What you have to do? You have to first write it in this way: 1 plus x cube. And wherever there is 1, we have to put a XOR, except this one, the final one. So 1 x, there is no x square, there is 0, and x cube. So put a XOR, except this, right? And in between, just put a flip flop or shift register. And this is P naught, P1, P2. So you will see that the corresponding parity will be 001 for the data word 0110. So just solve this, try to solve this. I'm just try to make the table and try to see what are the values of P2, P1, P0. It is a very interesting way to solve this cyclic codes, to implement the cyclic codes. So now what we have done till now, we have seen the cyclic codes can be generated using generator polynomial, and then we can find out its corresponding GX. For the systematic cyclic codes, we have done that we will derive G generator matrix, and then using this formula, we can find out the value of each code word corresponding to that data word. And how will we implement this in hardware? We have also seen that using the shift registers and the modulo 2 operation. Now the question is, how will these cyclic codes correct 1-bit error? Because you remember 7,4 bit can correct how many bits? We have to first see d min is equal to 2t plus 1. And by seeing, because we have already seen that d min is 3 for this case, so t is 1. So we can, correct? Because d min is minimum weight of a cyclic code, because cyclic codes are subclass of linear block codes. Always remember. So whatever properties linear block codes had, cyclic codes also have those properties. So whatever property is same as which we have done in the previous class. So minimum weight for cyclic codes also the minimum distance, because they are also linear codes. So by using that, you can say it can correct one bit error. But how will it correct the one bit error? Let's see it. So let us, for example, you transmit C and in the channel error introduces and your R is C modulo 2E. So received word is code word plus error, correct? Similarly, as you have represented your code word with Cx, code word polynomial, you can also represent your error with the error polynomial. So let us, so Rx can be written as Cx plus Ex. Received word polynomial is code word polynomial plus Ex means error polynomial. So what we do, we first check whether your remainder of Rx by Gx, whatever vector received polynomial, first you receive some R, okay? And you just make its corresponding Rx, that is easy, as I have told you, if you receive this 1, 2, 3, 4, 5, 6, 7, because it is 7 bit, 1, 2, 3, 4, 5, 6, 7, its corresponding, how will you make its corresponding polynomial? X plus x square plus x to the power 6. This is corresponding polynomial, right? Because this has location and value. So location is given by x to the power, right? And the values are given by this. We have to also write one, sorry, excuse me. Because 1 into x to the power 0, correct? 1 into x to the power 1, 1 into x to the power 2, 0 into x to the power 3, 0 into x to the power 4, 0 into x to the power 5, 1 into x to the power 6. So only these will be ones. Wherever there are ones, those terms will exist, other will be zeros. So once you receive your R vector, you first convert it to its corresponding polynomial and you try what is the remainder of Rx by Gx. So if the remainder is 0, there is no error, and if there is remainder is non-zero, and whatever value it gets is called syndrome polynomial. It is quite similar what we have done in the case of LBC, where we achieved syndrome. Here we are getting syndrome polynomial. Okay. So this syndrome polynomial, whatever we receive, this syndrome polynomial gives you the location of error. So let us do it with an example. Okay. So first, if you are given that you are using a 7, 4 cyclic code with generator matrix x cube plus x square plus 1. So how will you detect one error? So first you have to make a decoding table at the receiver. So receiver first make a decoding table. So this can be asked in the question, what is the decoding table of a 7, 4 code with gx x cube plus x square plus 1 or x cube plus x plus 1. That, so here we are making this decoding table for gx is equal to x cube plus x square plus 1. So for this, what we do, we first write the error, 1-bit errors. What are the possible 1-bit error patterns? Because it is a 7, 4 code, we transmit a 7-bit code word and there is an error. And 1-bit error means any of these 7 place will be 1. So just there are 7 possible error patterns, 1-bit patterns. So just write its corresponding error polynomial. It is easy. I have told you 0, 1, 2, 3, 4, 5, 6. Only 0 at x to the power 0 is 1. Here only x to the power 1 is 1. Here only x to the power 2, 3, 4, 5, 6. So these are its corresponding error polynomials. Next, what you do? You divide your ex by gx, where gx is your generator polynomial. So once you divide it, the remainder you write here. I will just divide for one case. For example, let us divide for x square. X square is same as x cube plus x square, because if you divide it with x square, its remainder is x square only, because 5 divided by 2, the remainder is 2 only, something. So you can remember it with this analogy. Because x square has a degree which is less than 3. So this is the remainder only, right? There is no point of dividing. Now we divide x cube with x cube plus x square plus 1 in order to get this. So we write 1 x cube plus x square plus 1. So what is its remainder? Remainder is x square plus 1. So once we get all of these entries for the remainder ex by gx, we write its corresponding vector. This is syndrome polynomial, as I told you. So we just write its corresponding syndrome vector. It is 1 means 0, 0, 1, correct? Because syndrome polynomial has, if you remember, 3, it is only 3 bit, right? Okay, just this point I will clarify. So Sx is remainder of Rx by Gx. Remainder of Ex by Gx, or so it is n minus 1 degree, it is of n minus k degree. Okay, so syndrome will be k minus 1 degree, correct? So k is 4 minus 1 is equal to 3. So there are 3 bits in the syndromes. So you can see also the maximum power is x square. It means 3, 0, 1, 2, 3. So the maximum power is 3. You can see. So the syndrome has 3 bits here. So you can write 1, 0, 0. X is, you can think it like that, that 0 into x square, 1 into x, 0 into, so 0. So 0, 1, 0. You can think it like that. 1 into x square, 0 into x plus 0. So 0, 0, 1. 1 into x square, 1 plus 0 into x. So here 0 into x. So it is 0. So similarly, you can find out what is the syndrome vector. So just once you have the coding table at the receiver, now you will see what is the received vector. So let us say that your received vector is this. So what you do, you make a corresponding received polynomial and you divide your Rx by Gx. And whatever remainder you get, you can do one thing. This is your x square plus 1. Just try to map it with here. So the steps is, if somebody in the question in the exams we ask, what is the code word corresponding to the received vector R? So first we have to make it like this, that your received vector R is this, its corresponding received polynomial is this. So once we get the polynomial, and we know that we are using a 7, 4 cyclic code with generator polynomial this. So we have already made the decoding table. Because at the receiver we have decoding table, then only we can decode using R that, whatever our C was. So once we get this Rx, we divide it with Gx. We divide it with Gx, and whatever remainder we get, this is syndrome polynomial, right? The syndrome polynomial we already have here, the syndrome polynomial. So we see the syndrome polynomial is x square plus 1. Okay, one more thing. If the remainder were 0, then we will say there was no error. So the code word we have transmitted is exactly received right. There is no error. But since it is not 0, the remainder is x square plus 1, we have to see the decoding table. So first you divide your Rx with Gx. If the remainder is 0, you say your C is R. There is no error. But if there is no, the remainder is some value which is syndrome polynomial, we go to the decoding table and we see the syndrome polynomial matches with the fourth row, and we check what is the corresponding error is x cube. So now we say that our Rx is Cx plus Ex, since you have, you know what is your Rx, x5, s6, s3, 2, 1, 1, 2, 3, 5, 6. 1, 2, 3, 5, 6. Your Cx is this, your Ex now you know is x cube. So just write it here. So your Rx is your Cx plus Ex, your x cube cancels. So what is your new Cx? Now you know your Cx is x6 plus x5 plus x square plus 1. So you can write this in the vector form 1, 0, 1, 3, 4, 5, 6. So this was your code word. So you say that the third bit is in error, the fourth bit is in error, because you have seen that your Ex is x cube and corresponding error vector is this. It means fourth bit is in error, and now you have your code word that is 1100101. So if the code word is 1101101, 1100101, what is its corresponding data word? Because we know, because we are using systematic cyclic codes, this is the data word, and these are parity bits or that data bits and parity. So it's corresponding these 1100. So this is your information, message or data bits. So this is the whole thing which we have to remember for the cyclic codes. So cyclic codes, once somebody says cyclic codes, get Gx, and if somebody asks to use a systematic cyclic code, then you get G generator matrix with this concept, that we will get the rows of the parity, because G is I comma P, we know I, we just need to know the rows of P, which can be found out by using this formula. So once we get G, we get the encoding table. This is the first step. And then we have studied the encoding circuitry, correct? Now we know how to decode it. We receive some R, we try to find out the remainder or the syndrome polynomial, that is remainder of Rx by Gx. If it is 0, no error. If it is not 0, there is error. And which which bit is in error, we have to find using decoding table. Decode formation of decoding table I have already discussed. So this is the whole lecture for the today class. If anybody has any doubt, he or she can ask. Okay, so I assume that there is no doubts. So we will meet in the next class. Thank you.